Hello everyone, my name is Haley Rylander. I'm the Extension Support Specialist with the GLASE Consortium, and thank you all for joining this last webinar of the GLASE 2021 series. We've had a really good series and we're grateful to all of our speakers and our listeners for joining us this past year. So be sure to look out for the next series in 2022 that will be starting up here in a couple of months. And as always, that will just cover a broad range of topics related to controlled environment agriculture. Before we start the webinar, I would like to extend a huge thanks to our current GLASE industry and CEA members for their support. It's because of them that we can promote activities and offer them to a wide range of audiences. So let's start today's presentation. I would like to introduce our three speakers for today: Dr. Kale Harbick, a research agricultural engineer at USDA-ARS, Michael Eaton, a research support specialist at Cornell University, and Dr. Tim Shelford, an extension associate at Cornell University. All three are regular GLASE contributors and speakers with a lot of knowledge between them, and they are going to be sharing with us today about lighting and energy modeling in controlled environment agriculture. I encourage all of the attendees today to make use of the Q&A box at the bottom of your screen throughout the presentation, and those questions will be addressed at the end of the webinar. So with that said, I'm going to hand things over to our presenters.
All right, thanks, Haley. Hi, everyone. I'm Michael Eaton. Actually, I'm trying to share the screen, and it says host disabled, participant screen sharing. I don't know if you could make me co-host or something.
You're good now, Michael. Sorry about that.
Cool. No worries. All right, here. Okay, can you guys see the correct screen?
We're seeing both your views, Michael.
There you go.
Okay.
That's good.
Let me just move the video thing out of the way. Okay. No, still away. There we go. How do we go back? Sorry, technical difficulties. Alrighty, here we go. Hi everyone, I'm Michael Eaton. Today I'm going to be talking about light and energy modeling in controlled environment agriculture. So the work I'm presenting today is part of a larger project that was dealing with the economic and environmental footprint of scaling up urban CEA. So looking at greenhouses located in the city, plant factories or warehouse farms that are completely enclosed, that don't have access to natural light, and a third facility type called a skyscraper farm. So as far as I know, these don't exist, but they have been proposed as a way to maintain high space use efficiency while accessing some natural light. So the research aims of my contributions to this project were to compare the resource efficacy of CEA facility types. And specific objectives were to model the natural light resource in vertical farms and greenhouses, and also quantify the energy consumption associated with each facility type for different locations. And today I thought I would present mostly on vertical farms or skyscraper farms and plant factories because they both involve light and energy modeling. So the light modeling approach I used is ray tracing. It's a form of climate-based daylight modeling. So that means I use meteorological data as inputs for the light model. And ray tracing is a computational technique that can simulate the lighting conditions in a space via mathematical description. And many times we are interested in generating spatial distributions of light within buildings, and so to do this, we discretize the surfaces of the building into grids, and then calculate the lighting levels at the center point of each grid. Not sure how many of you caught my presentation for the GLASE lighting short course, but I showed this video here. So what this is a time-lapse video of a research greenhouse on Cornell campus on the left, and a computer model of the greenhouse on the right, and we use for lighting simulation. And as you can see, the shading from the structural members and the light fixtures move across the space in the model, very similar to how it happens in the time-lapse video. So this can kind of give you an idea of what light modeling is about in a short time period. And now I'm going to be talking about light modeling in vertical farms. So one of the first questions we wanted to ask was how much light is actually entering into the growing space? Because I guess proponents would say that introducing transparent glazing will cover the lighting you need for growing crops. But is that true? And also, how much does this vary with the geometry of the building or the location? And finally, the cash value of this is what are the energy implications of this light availability? So to study this question, we came up with a scenario called skyscraper farm in a field, which refers to the fact that there are no surrounding buildings in this model. So there's no shadows cast by neighboring buildings into the skyscraper farm. So what we did was simulate the lighting conditions in these 5 buildings for a year long at hourly time steps for 2 locations, New York and Los Angeles. And we wanted to look at how much energy each of these buildings would require to maintain a set lighting target. So in order to maintain a daily lighting target of 17 moles of light per square meter per day in the vertical farms, this is how much energy each building would use. So the plot shows on the y-axis, the vertical axis, lighting energy consumption, and the horizontal axis are the different models. So I'd like to draw your attention to the far right, where we have a plant factory lighting energy consumption. So if you don't have access to natural light and you are providing 100% of your crop lighting to meet 17 moles per day with electric lighting, and you have an assumed lighting efficacy of 2.0 micromoles per joule, you'll require about 862 kilowatt hours per square meter of canopy to meet that lighting target. And I think this lighting efficacy is present day. And I know some manufacturers report up to 3 or even higher than 3 micromoles per joule, but this is a pretty typical value for present day technology. And what's interesting here is that the vertical farms modeled here use about 15% less lighting energy than a plant factory, but 4 to 10 times more than a greenhouse. So the total energy picture is a lot closer to that of a plant factory than a multi-level greenhouse. So the next question was we wanted to ask was how much do surrounding buildings affect the lighting conditions in vertical farms? And to answer this question, we came up with another scenario called skyscraper farm in a city, where we generated 9 urban contexts, so varying the size and the spacing of surrounding buildings to see how much the shadows cast by surrounding buildings affect the lighting conditions in the space. This is just an up-close shot of one of those scenarios, and I also took away the walls of the building so you can kind of see how the lighting diminishes towards the lower floors of the skyscraper farm. And that's exactly what we find when we do the math. So this plot here shows on the vertical axis the mean daily light integral in the space, and the horizontal axis the level of the building, so each floor of the building. And I'm sure the legend is not helpful without the diagram of each scenario, but to orient you to this plot, you can see that the lowest curve there with blue markers should correspond with the densest urban scenario. And the green curve at the very top that's almost flat corresponds with an urban scenario that is less densely packed. And interestingly, for both LA and New York, the average light received for all the lower levels is quite low. It's less than 2.5 moles per day for LA and less than 2 for New York City. And this is low compared to the requirements for crop lighting. So lettuce production can take up to 17 moles per square meter per day. Next, we wanted to look at how this fits into the total energy picture of vertical farms or plant factories. And so to do this, we have to model the thermal fluid systems involved in controlling the environment. So the production area will likely control the temperature, humidity, light, and potentially CO2. And to do this, you need an HVAC system. And here shown is a VAV unit, a variable air volume unit, with a water-cooled chiller and a hot water boiler to condition the air before it's supplied to the growing space. And optionally, you can include an air side economizer that uses outdoor air to cool the space when it's advantageous. Another component to the energy model is the evapotranspiration submodel. So plant evapotranspiration will affect the conditions in the space, and it is sensitive to the temperature, the humidity, or the vapor pressure deficit, the airflow in the space, which determines the boundary layer thickness on the leaves, radiation, stomatal resistance, leaf area index, and I think there are others, but it's sensitive to a lot of variables. And I don't have time to go into the specific model I used. Some famous models are Penman-Monteith, and I think many people here might be familiar with that model, but I thought I would just jump into some results of work that is in preparations. So I looked at a plant factory and a vertical farm in LA and New York, each with a 1 acre footprint, growing 1 layer of lettuce with and without the use of an economizer, air side economizer. And from what we see, the plant factory in both locations, LA and New York, use the most energy because they're providing 100% of the lighting for the crop growth. And the next bar up from the bottom is the New York City vertical farm or skyscraper farm, which is basically our same plant factory model, but introducing transparent glazing on the outside, the walls. And the energy footprint is lower, but not as much lower as you'd hope after introducing a transparent glazing or building an entire skyscraper just for growing lettuce. The next bar up from that is if you introduce an air side economizer, you can reduce the cooling load a bit of the space, but if you're using outdoor air from New York to cool the space from all the heat generated by the lighting, you may actually have to heat up the air before you supply it to the space because it's winter air. You can't supply very cold air to your plants, or it might affect the growing conditions. So you incur a bit of a heating cost. And the same is true for the vertical farm or the skyscraper farm. And an additional consideration for energy efficiency is introducing CO2, elevated CO2 levels into the growing environment. So to get the same growth rate for 17 moles of light, if you introduce an elevated level of CO2, you can provide lower lighting conditions in the space and maintain your productivity. And so I consider a combination of elevated CO2 and different lighting efficacies in this study here that is just looking at a plant factory in New York City. So this scenario has a 1 acre footprint with 10 layers of lettuce growth here, and looked at 3 different lighting efficacies, 2, 2.5, and 3 micromoles per joule, with elevated CO2 concentration of, one scenario is ambient at around 400, and the other is 840 ppm. And I chose that number because at 840 ppm, the amount of energy savings you get from raising the CO2 concentration will be equal to the amount that you get by increasing the lighting efficacy. So it's just a convenient number to choose to get the same kind of energy footprint. So let's start at the bottom here. Our baseline plant factory uses about more than 4,000 megajoules per square meter of canopy, and then you can lower the energy consumption with different design configurations. So if you increase the lighting efficacy, you can lower it. If you introduce an economizer, you can lower it. If you increase the CO2 concentration in the growing space, you can lower the necessary amount of lighting. And so the savings potential are significant with considering these energy efficiency measures. This is preliminary work, so keep it between you, me, and 100 other people here. So it's before peer review, but this is what the total energy footprint is looking like. And if you convert this to emissions and consider variations, including the use of an economizer or using a plant factory or a vertical farm, you can see that different areas of the US have different emissions associated with production. So I modeled 5 locations here: New York City, LA in green, Chicago in red, Atlanta in yellow, and Seattle in gray. Okay, I think that's all I have today for time, and I welcome any questions after the presentation. Thank you.
Can everyone see my screen?
Looks good, Tim.
Great, thanks a lot. Thanks, Michael. I'm going to talk today a little bit about what I've been working on and with the day-ahead market price of LASSI, and a little bit of a tool that we've developed at Cornell, online LASSI, that Michael has also been working on. Let's see here, next slide. Here we go. We talk a lot about LASSI, and it's an acronym for a lighting control algorithm that was developed at Cornell by Professor Lou Albright in the 90s to help with the lettuce production that they were testing at the time. And it stands for Light and Shade System Implementation. And basically the purpose of LASSI was to get a uniform daily light integral, the amount of light that the crop receives every day, so that you could have the same amount of growth throughout the year, which would increase the sort of predictability in your production, so make it much easier to market things. And another goal was also to shift the supplemental lighting into cheaper off-peak periods of the day, which are usually the night periods. So the way that LASSI works is it takes a measure of what the natural solar radiation is from a sensor, and based on that, it can make predictions about how much light the crop will have received by the end of the day, or what the natural daily light integral will be. And it tries to delay decisions about turning on supplemental lights until it makes the decision that it really has to be able to start lighting now to meet the daily light integral target. And so by delaying those decisions, it gains more information, and the predictive ability gets better. So, and one benefit of sort of delaying this is that it does shift the lighting into the later hours of the day, off-peak electricity times when the prices are considerably lower. And it also takes into account some shading abilities. It uses that same predictive ability to know that, well, today is going to be a really bright day, so we better, pull the shade so that we don't get too much light on the crop, which is a very important consideration in a crop like lettuce where it can be damaged by too much light, unlike other crops like tomato, which usually benefit from as much light as they can get. Now, the original algorithm was developed for use with high-pressure sodium lights producing lettuce. And the characteristic of high-pressure sodium lights is they don't really like to be turned on and off on a regular basis. So usually you want to turn them on. There's a 10-minute warm-up or so, and you want them to stay on until you're finished with them. You don't want to be turning them on and off every hour. So the next version of LASSI, or another version of LASSI that we've developed, is called the day-ahead market price LASSI, DAMP LASSI. We've also called it DAM LASSI, just day-ahead market LASSI. And it's sort of another step to it where we want to take advantage of something called day-ahead market pricing, which is an electricity pricing that might be available. And it's basically that the utilities have some cheaper rates available if you're willing to, join that program. What they do is, so here's a picture of a plot of the average load for an area of New York, or maybe it could be the whole state of New York for 2008. And we can see that across the whole system, the average load is about almost 19,000 gigawatt hours, whereas the peak load gets up to a high of about 32,000 gigawatt hours. And so there's quite a difference between the peak and the average. And it's kind of hard to see from this graph, but only 90 hours of the year account for 10% of the peak demand. And so those hours, it's very expensive for the utility to provide electricity. And so they'd like to, avoid people using electricity during that time. And so they offer this program, this day-ahead market pricing, where 24 hours in advance, they publish the hourly prices for electricity because they kind of know, based on historic data and oncoming weather, what those prices are going to be. And so if you agree to do that kind of pricing, you can take advantage of some very low electricity costs. And so that's what the day-ahead market LASSI seeks to take advantage of. So this is a plot of how just regular LASSI works on a typical day, and we can see the yellow bar is the natural solar radiation. We can see it gets some natural radiation, and then this is sort of during the day, and then it makes the decision that it has to start lighting to be able to hit the 17 mole target by the end of the day. And even though it's not quite into the off-peak period, it starts lighting, and then it hits the end of the off-peak period, and the target is hit. So with the day-ahead market price LASSI, it's sort of the similar kind of idea, except that the day-ahead market algorithm searches for the cheapest hours during the day and applies light then. And so we can see on that same day, just with the day-ahead market pricing, the prices are a lot lower, even during the peak time. But LASSI, the new algorithm, starts lighting even before the other one did, so early in the day, and then it lights throughout the day later, but also achieving the 17 mole algorithm. Target. So comparing how these two algorithms worked, I looked at 3 different locations in New York that get kind of differing levels of sunlight. Islip is on Long Island, for those who don't know, and gets a lot of natural light. Buffalo is usually has a lot less light because of the lake effect, and Albany's sort of in between. But so I looked at 4 years, and sort of these are the savings we got. So one thing to notice is that the day-ahead market LASSI does use or tend to use more hours of lighting per year than LASSI, and that is because it is lighting earlier in the day, and there are some cases where it's overshooting a little bit. So it is using more hours of lighting. However, the cost of providing that lighting is much lower. And then that's just due to the fact that you can take advantage of the really low prices for day-ahead market pricing. It should be noted that there's always a risk with that type of lighting because the electricity costs could spike. However, the spikes in electricity are usually in the summertime, and that's usually not when you're applying supplemental lighting. So it seems like a pretty good way to save a lot of potentially a lot of money on your lighting. And as I say, this is an algorithm that we're testing at Cornell, and hopefully we'll be able to get it out to commercial or to testing it in the future. So the next thing I'd like to talk about is a tool that Michael and I have been working on at Cornell, and that's to sort of bring the ability to test out how a LASSI control algorithm would perform either in an existing greenhouse or a proposed greenhouse. We talk a lot about the benefits of it, but we wanted to be able to give it, provide a tool for people to be able to run different scenarios and actually see how it would perform, and which would hopefully help them inform in making some decisions about their lighting system. So one of the things that it will give is, the days in which the crop's daily light integral requirement are achieved, the energy consumption, the operational costs. And then we've also put in some different lighting control technologies so that you can compare LASSI to a threshold control. So the website is onlinelassi.org, but I should note that it's still very much in a testing mode, and please don't all log on and try to use it at the same time. It's still definitely being tested. So we'll certainly let you know as soon as we're confident that everything is great. But just a little bit of a warning there. So so this is what we usually see when you land on the page. And I'm just going to quickly go through a case analysis of one way that you could use it. So say we have a greenhouse in Binghamton, New York. We can put in the size, the target DLI, some characteristics about the lighting system, and some about the electricity rate. Again, so we're just using a simple on and off peak rate, like the original LASSI, as well as the demand charge for the electricity. So after putting in all the information, you get a summary of what you've input, and then you can run the simulation, and you get monthly reports and as well as annual values. So for each month, how many kilowatt hours are used for the lighting, what the average daily light integral was, and how many hours that took. So you also get a plot of the performance, and here we can see just how well the algorithm performs. So here the orange line is the target daily light integral. The blue line is the integral outside of the greenhouse, and so you can see that in the summertime it varies very high, and in the wintertime quite low. And then the blue or the green dots are the actual achieved daily light integral. So you can actually see how important the shading system is in keeping the integral at 17 moles. So for this case analysis, we use the characteristics that we had before. We can see what our lighting was. Now, if we ran it again and we said, we want to try, a more intense lighting system. So rather than having 180 micromoles, we're going to have 220 micromoles at the crop. It's going to take more lights using the same equipment, but it's going to reduce the number of hours that we need to run it, which in turn reduce the on-peak hours. And so, we're going to have a little bit of savings, maybe a little bit of power savings, but not a ton. And so in the next case, let's look at using a different technology like LEDs with a much higher efficacy. So the output of the crop is the same, the size of the lights is reduced, and the performance is all the same. The number of hours used is the same. However, the electricity costs are down, and the demand charges are down. And here we can see we result in quite a saving. So you could then use that, to determine whether, the payback period for LEDs is worth it or not. there's a lot of different ways that we think this tool will benefit the industry, but that's just a really quick overview of what we're planning and working on with it so far. So as it becomes available, we'll be sure to send out a lot more information. So I think that was all I wanted to talk about today. So with that, I will pass it over to Dr. Kale Harbick. Thanks a lot.
Thanks, Tim. My slide shows up okay?
Yes.
So I wanted to tell you a little bit about upcoming tool we have called Virtual Grower version 4. But first, just a little bit about why we care so much about energy modeling. So in CEA, it's a pretty important thing to look at because it's a very significant cost for both greenhouses and plant factories. You can do some nice things with it, such as you can estimate the energy consumption and cost for an operation before the building is even built. So you can compare, some different design choices before you even break ground. It's useful for sizing your HVAC equipment, such as boilers or ventilation equipment or cooling equipment, and also lighting. You can model the effects of climate change by using the appropriate weather files. You can do a cost-benefit analysis if you already have a building and you're thinking about upgrading your lights, for example. You can model what that would look like in terms of energy use and cost and payback time. And if you have enough information from multiple operations, you could also do benchmarking to see where you compare to others. And this is very common in the commercial energy sector for buildings like hospitals and grocery stores. So Virtual Grower is a tool that lets us do energy modeling, and it's specifically designed originally for greenhouse production. So it looks at greenhouse energy consumption and cost. Again, you can assess the effects of retrofits on energy and profits, and it was developed at USDA-ARS. Originally, it was released in 2006 with Jonathan France as the lead. And over the past several years, there's been many improvements to it. It became PC and Mac compatible with many more climates added in. A multi-language option was included in the most recent version, which is 3.1. And at that time, Jennifer Bolt was the lead scientist on it. There was quite a gap from then till now in terms of development because there were hiring freezes in place, but now we have a solid team in place. So Jennifer and I co-lead the project, and we have a programmer hired last year named Yahya, who has been hard at work updating the program in preparation for our version 4 release. We also have a vacant position, engineering technician. So if anyone's interested in that, feel free to contact me. In terms of architecture, traditionally the program was a Java application that you had to download. And so every time we changed it, you'd have to re-download it. But we're going to a fully online version with version 4. It'll be compatible with most web browsers. So you just run it right in the browser, which is nice because anytime we update the software, you'll be able to have the most recent version just by refreshing your webpage. So lots of new features we're going to include, which I'll mention in a second, and we're hoping for a 2022 release. So some of the features we're planning to include, we want to make the energy modeling calculations more robust and compliant with ASHRAE standards. ASHRAE is the organization that makes standards relating to air conditioning and heating. So we want to comply with that. Include all TMY3 weather locations. So TMY3 data is a weather file format that's available for over 1,000 locations in the contiguous US. So all of those will be included. We would like to have the ability to both save your files on the cloud and locally. So for example, if you save your files on the cloud, you can access them from any computer, and they'll be in a centralized location, or you can back up your files to a local file. We're going to include additional cultivars. Traditionally, a lot of floriculture crops have been in virtual grower. We're going to expand that to vegetable crops and a few other things. Multiple heating, lighting, and control system types will be included. So HPS and LEDs for the lighting side, many different control strategies on the lighting side. So, on-off control, hourly schedules, threshold control, and daily light interval control. A new feature that we'll have is the ability to have two models side by side for comparison, two or more. So you can have some settings for a building and then have a second model with different settings and then compare them side by side to see which one would result in the least operating costs. So included will be the cost of natural gas, electricity, demand charges, and CO2 costs in case you're doing CO2 supplementation. So the full utility cost picture will be present. We also want to model plant factory systems. So, some growers may be considering whether to build a greenhouse or a plant factory in a particular location. They could design both systems within the tool and then compare them side by side to see what the energy and cost picture would look like. So right now, our programmer has done a significant amount of work on the interface, and that's nearing completion. We still have a lot of work to do under the hood with the calculations, but like I said, we hope to have this tool available sometime next year. So I'll wrap it up there, and happy to take questions along with the other panel members. Thank you.
Thank you, all three of you. That was really awesome. So if anyone has questions, please submit them now in the Q&A or in the chat. I can get us started. For Tim, how widely used is LASSI and also the both types of LASSI, I suppose, in commercial greenhouses right now?
Sure. So the day-ahead market price LASSI is just been an academic exercise at this point. We wanted to test the proof of concept, and so it's just been tested on the computer, and I think there's quite promising results, but we have yet to prove it in the real world, in a real world situation. In terms of LASSI being used, that's also something that's it's not as widespread as we'd like it, even though it was developed in the 90s. The commercial uptake has been pretty slow. We have a couple of demonstration modules that are our partners with in the GLASE project, where we're demonstrating LASSI, and the hope is that we'll write some case studies of that to show the benefits. And there's a new company, Candidus, of which Eric Omatos is the president, is getting ready to demonstrate LASSI at I believe 8 more greenhouses in the coming year. So it's starting to get out there. There is a similar type of algorithm that the control company Argus does. It's I don't believe that it controls shades though, but it is a daily light integral controller that does try to control to a target. But I don't believe it does shades.
Great, thank you. So from the Q&A box, thanks for your presentation, very interesting. Is CO2 gassing the only viable option for CO2 supplementation considerations?
Some people do tank supplied CO2 as opposed to the off gassing of combustibles inside the space. So they're both, I would say they're both viable. Which one is more economical depends on the CO2 prices you're able to get in your area compared with the natural gas or whatever fuel you're using, those prices. Another difference is, of course, if you're burning fuel and off-gassing in the greenhouse, you get some other chemicals that you may not want, like ethylene and nitric oxide and other things. So the effects of those things is still being investigated. And Cornell actually has a project to look at that sort of thing. But yeah, there's multiple options.
I also another way that you can supplement with CO2 is in the wintertime you usually use a boiler for heat. So they'll often run the boiler during the day, even if they don't necessarily need the heat, but they'll generate the CO2, which they can recover and pump into the greenhouse, and then they'll store that heat as hot water that then they can use it at night to provide the heat when they actually need it. And we actually have another version of LASSI that takes account the effect of CO2 on growth, and that's another thing that's being tested or will be tested in the demonstration modules as well. So,
great. A question about LASSI. Are there plans to adapt LASSI to tunable LED fixtures?
Yes, we're working on a so-called real-time LASSI, which will take advantage of the dimmable ability of LEDs. I forgot to mention in my presentation too that the day-ahead market version of LASSI actually works quite well with LEDs and their ability to be turned on and off, for the specific hours of the day that you might have cheaper electricity, which you wouldn't really want to do with the high pressure sodium. But we've certainly been looking at the dimming abilities of LEDs, but not so much the different spectra.
Thank you. Another question, I'm curious how day-ahead marketing pricing will work with high supplemental light levels. We design cannabis facilities and provide 800 micromoles of supplemental lighting in the winter. Worried about the algorithm may recommend the lights run based on cost savings while it is sunny and end up providing too much light certain times of the day. Is this a common problem?
Sure, yeah. And so usually with LASSI, it predicts if it's going to be too bright a day, and it will require that the shades close, and it would disable lighting during that period. If you are doing a cannabis facility though that's not in a greenhouse, I think the day-ahead market pricing might be not necessarily for you, because you're going to be providing or needing to provide light throughout the year, and you could be nailed by some of those peak prices during the summer months. Yeah.
And you mentioned, Tim, in the greenhouse case, typically in the peak summer lighting season is when you have peak electricity prices.
Yes.
Because of air conditioning, but that's when you're not needing to provide as much light. So
exactly.
In the lower light portions of the year, which is what you would use, it should work pretty well.
Yeah.
All right. Are there any test installs or experimental installations of LASSI, particularly in New Jersey, but just like around, that people could see as demonstrations?
We do have 2 pilot facilities where we're testing LASSI, and as I mentioned, in the coming year, there's going to be 8 more locations, all within New York State, because it's all been sponsored by the New York State Energy Research and Development Authority, and their project is in New York. So one of the facilities is in Buffalo, and the other is in Berlin, New York.
All right, thank you. I just have a general question that each of you could answer. So what further research and energy models do you think will be most useful moving forward? or improvements upon what is already available?
Yeah, sure. I'll start.
Oh, go ahead.
Thanks, Kale. Well, I think some future research at Cornell for the work that I presented on could be examining trade-offs between certain design configurations. For example, if you use an airside economizer, you might not want to supplement with CO2 because you're at that point you don't have a closed system, and you might run through CO2 much quicker than you want to, which could be costly. So examining interesting trade-offs in design options, as well as looking at kind of trade-offs in investment for lighting efficiency. So if you invest in higher lighting efficacious fixtures, how quickly does that pay off? So CapEx versus OpEx. And those are just some research topics we're looking into, as well as what are the emissions associated with production for different facility types for different crops. So we've done lettuce ad nauseum, but we are looking now at tomatoes and strawberries.
Yeah, I think, we've in some sense barely scratched the surface with CEA energy modeling. I mean, the commercial building sector has many decades of experience in this field, with HVAC design, and designing buildings for human occupants is very, very different problem than designing buildings for plants. Plants give off a tremendous amount of moisture, which has very big energy implications. And as Michael said earlier, it's difficult to model evapotranspiration because it's affected by so many different things, and it's cultivar specific. So, I think a lot of research can be done in improving the accuracy of the models, but of course the models are only as good as the inputs you put into them, and we need to know a lot more about how plants interact with the energy balance of the building.
Yeah, no, I totally agree with Kale and Michael. And I think one of the areas at Cornell where we've been working on is the relationship between supplemental carbon dioxide and light. And, we have a lot of long tradition of working with lettuce. And lately we've been doing tomatoes and strawberry. And I think we've just recently started on hemp, but there's other crops certainly that we need to figure out that relationship, the benefit, what levels of CO2 does it make sense to supplement to, and light levels. And then I think, like what Kale's been working on with ARS and the virtual grower, and what Michael and I have been doing, sort of bringing these models out to the public so that they can really be used. There's a lot of modeling work that goes on that just kind of dies because it's in an academic journal, and it's not really that easily accessible to the average user. I think bringing this research into an online tool, or a tool that's available to download and giving it to the public to use, there's a lot more that can be done on that, and expanding the capabilities and different things to model, and it's certainly come a long ways, but there's a lot more we can do.
Yeah, great. We have another question. So how important are dehumidifiers for the energy balance in CEA?
I think this is a big one. So, one number that I like to throw out is if you're growing head lettuce optimally, it would produce something like 4,000 gallons of water per acre per day, every single day. And in a greenhouse, we get rid of that moisture by blowing it out the window. We have fan and pad cooling systems quite often, and we just ventilate all that moisture out continuously or frequently. But in the plant factory case, in a warehouse farm, it's more common to use mechanical cooling systems where you're condensing that water onto cooling coils and then, draining the condensate. So it takes a considerable amount of energy to do that. And in some cases, it can take more energy than the lights themselves. So proper dehumidification is very important for, optimal growth and disease reasons. And it has a very large impact on energy consumption.
All right. Well, if we don't have any other questions, thank you so much for all three of you. Those were some really awesome presentations and some good discussion. So if you want to hear more about any of this, we have some of these resources on the GLASE website. And thank you all for joining.